Welcome to Advanced Higher Physics. This is Unit 1, Rotational Motion and Astrophysics. Unit 1.1, Kinematic Relationships, Part 2. So, what delights await you in Kinematics Part 2? Well, here we are. You'll learn how to calculate the instantaneous velocity as the gradient of a displacement time graph. You'll also learn how to calculate the instantaneous acceleration as the gradient of a velocity time graph. And finally, we'll look at how to find the displacement using integration to find the area under a velocity time graph between specified limits. Looks good. And so we begin by considering a simple velocity time graph as shown. Before we proceed in analysing this graph, an important instruction. You're going to be asked to answer some questions and solve some problems as you watch this video, and to gain most benefit you really do need to make sure you don't look at the answers before answering the questions yourself. So when you get to the point of forming an answer, press the pause button, decide on your answer, show you're working, write down you're working on paper, reach your final answer, and then restart the video. So, to begin, a simple question. Describe the motion represented by the graph shown. Pause the video now before answering. And the answer is, this is a uniform acceleration. A motion you will be very familiar with from previous studies. Question 2. Write down an expression for the gradient of this graph. Again, pause the video. The gradient is given by the change in the y-coordinate divided by the change in the x-coordinate. In maths, you might have called this y2 minus y1 divided by x2 minus x1. You could have called it delta y over delta x. Now, because our y-coordinate is velocity and because our x-coordinate is time, our gradient is delta v over delta t. Question 3. Are the terms in your answer to question 2 finite or are they infinitesimal? The answer is that they are both finite. They are not vanishingly small. And question 4. The gradient of this graph has physical meaning in the real world. You're all familiar with the mathematical definition of gradient, but in physics, the gradients of graphs of physical quantities often have real physical meaning in the real world. What does the gradient of this graph represent? The gradient of a velocity time graph, in this case delta v over delta t, represents the acceleration of the moving body. The more familiar form of the acceleration equation, of course, is v minus u over t, but delta v over delta t is just a different way of writing that familiar acceleration equation. Now let's look at a displacement time graph. The graph you see below of displacement against time represents precisely the same motion as that of the previous page. In other words, it's a uniform acceleration. And you'll remember from your work at higher that the displacement time graph for a uniform acceleration is a curve. Question 1. Describe the motion represented by this graph. Well, as was previously mentioned, it's a uniform acceleration. Question 2. Why can you not write down an expression for the gradient of this graph? Well, the answer is there is no single gradient which describes this graph. The gradient is not constant, it's changing. This graph gets steeper in gradient as time goes on. Question 3. Write down an expression for the gradient of this graph at a particular time t as shown. The answer is the gradient at time t is given by ds by dt. Are the terms in your answer to question 3 finite, or are they infinitesimal, that is, vanishingly small? Well, dt is by definition an infinitesimally small time interval, and so ds is also infinitesimally small. Finally, question 5. The gradient of this graph at a particular point in time has physical meaning in the real world. What does the gradient of this graph represent at a particular point in time? Well, the gradient, which is ds by dt, represents the instantaneous velocity of the body at the particular point in time at which we are finding ds by dt. Still looking at the same displacement time graph, on a piece of paper or in your jotter, sketch the graph as shown on the left. Pause the video while you do so. Now that you've sketched this displacement time graph, draw the tangent to the curve at time t using a ruler. Your tangent should look something like this. Could you now write down an expression for the gradient of this tangent to the curve at time t? The gradient, of course, is ds by dt, the same ds by dt we talked about in the previous slide. And now we come to an example. And firstly, an important reminder. It's especially important in these worked examples that you pause the video before making your own attempt at an answer. So let's consider a body undergoing uniform acceleration, not unlike in the previous slides. Could you now write down the general equation for its displacement s with respect to time t? The general equation is the one that would apply to all displacements as they change with time. Well, for a uniform acceleration, it's one of our equations of motion, number 2. S equals ut plus a half at squared. That is how the displacement of any body undergoing a uniform acceleration changes with respect to time. Part B. Let's imagine the initial velocity of this body is 20 meters per second and the acceleration is 6 meters seconds to the minus 2. Pause the video and write down the particular equation for this motion. Well, in this case, s equals 20t because u is 20, and a half of a is a half of 6, which is 3, giving us s equals 20t plus 3t squared. Now, using differentiation, find the equation for the velocity of this body. Well, velocity, of course, is ds by dt, so we take a d by dt of s. That's d by dt of 20t plus 3t squared. And when we differentiate 20t, we get 20, and when we differentiate 3t squared, we get 6t. So the velocity equation is v equals 20 plus 6t. At what time will the velocity be 44 meters per second? Well, we begin with our velocity equation. V is 20 plus 6t. We substitute in for 44, rearrange, and we find that t is 4 seconds. So 4 seconds into this motion, the velocity will be 44 meters per second. Finally, could you now differentiate the velocity equation to confirm that the acceleration is indeed 6 meters seconds to the minus 2? Well, differentiating the velocity equation gives us dv by dt. That, of course, is the acceleration a. So we do a d by dt on 20 plus 6t, and that gives us an acceleration of 6 meters seconds to the minus 2 as expected. We now consider a non-uniform acceleration. Look at the velocity time graph shown. How do you know that this graph represents a non-uniform acceleration? Well, a uniform acceleration would have a line of constant gradient on its vt graph. This line is clearly of changing gradient. In fact, the gradient is increasing. So this must be a non-uniform acceleration. Describe the behavior of the gradient in this graph. The gradient is clearly increasing with time. The graph is becoming steeper as time goes on. Now, using calculus notation, write down an expression for the gradient in terms of v at the time t as shown. The gradient is dv by dt, and dv by dt, of course, is the gradient of the tangent to the curve at time t, as shown by the straight line tangent. Again, using calculus notation, write down an expression for the gradient, but this time in terms of s displacement. Well, we know the gradient is dv by dt, and that can be written as d by dt of v. But what is v? Well, v itself is ds by dt. So we're essentially doing a d by dt of ds by dt, and that can be written d2s by dt squared. So d2s by dt squared is an alternative way of writing dv by dt. We're writing it in terms of s rather than in terms of v. That's called a second order derivative, and d2s by dt squared means precisely the same thing as dv by dt. It's just expressing the acceleration in terms of the rate of change of displacement rather than the rate of change of velocity. We're now going to consider a non-uniform acceleration and how to find the displacement of the body undergoing the non-uniform acceleration. So our graph is as before. As you can see, the velocity is increasing as time goes on, but in a non-uniform way. Well, question 1 is, why can we not use the standard equation of motion, s equals ut plus a half at squared, to calculate the displacement of this body after some time t has elapsed? Well, the answer is that all 4 equations of motion, including s is ut plus half at squared, apply only to motions with uniform acceleration. So this motion is a non-uniform acceleration, so we can't apply the equations of motion. That begs the question then, how do we find the displacement of this body after time t? Well, we know that the area under a VT graph is displacement. So the area under this VT graph will also yield displacement. How then do we find the area under a graph which is not a straight line? And the answer is we integrate the equation of the curve and we get the area under the graph using integration, just like you did in higher maths. Knowing that, can you now write down an expression for the area under this graph between t equals 0 and t equals t as shown? The area under the graph, we'll call it S, the displacement, is the integral from 0 to t of v dt. And this is shown as the shaded region on the graph. So integration is a very powerful tool in mechanics and indeed in many branches of physics for finding the areas under graphs where the area under the graph has an important physical meaning. I feel a worked example coming on. So, example 2. Before proceeding, a reminder, we're going to be answering some questions, and so make sure you do not look at the solutions before attempting to solve these questions yourself. Use the pause button after every question. So, the context for this example. Look at the graph. It's a displacement time graph. It's a graph showing the motion of a body, in this case a rocket, being launched from the surface of the Earth. The displacement is clearly increasing with time. Now, we can't assume just by looking at that curve that it's a uniform acceleration. In other words, that would be a y equals constant times x squared type graph. Without values, we don't know what the mathematical form of the function actually is. So we would need to be given it. In this particular case, the rocket's displacement for the first 3 seconds of its motion is given by this equation. S equals 8t cubed plus 4t squared. Now that does not fit into the standard s equals ut plus a half at squared type of shape. And so as soon as we know that equation, we can tell that this is definitely not a uniform acceleration. And you will be given situations like this where we have non-uniform accelerations involved. But the questions aren't too difficult, as you'll see. So, part A. Find expressions for the velocity and the acceleration of the rocket. Well, we are given an expression for the displacement s, and the velocity can always easily be found from the displacement by simply taking ds by dt. So all we need to do is to differentiate that equation with respect to t. When we do that, we get 24t squared plus 8t. That is the expression for the velocity of this body with respect to time. Acceleration, of course, is dv by dt. So now that we've got the velocity equation, if we differentiate again, we'll get an expression for acceleration. And when we differentiate 24t squared plus 8t, we get 48t plus 8. So we have our two expressions. Part B. After 3 seconds, find the displacement, the velocity, and the acceleration. All we're doing here is we're using the equations which we now have for s, v, and a, and we're simply substituting in a time value of 3. So the displacement equation is 8t cubed plus 4t squared. We substitute in a value of time of 3, and our displacement turns out to be 252 meters. So this rocket has ascended to a substantial altitude even after 3 seconds. Now the velocity. Well, the velocity equation is 24t squared plus 8t. Put in our time value of 3 seconds. And we get 240 meters per second. It's accelerated quite rapidly during those 3 seconds. And finally, the acceleration equation is 48t plus 8. Put in our 3 second, and the acceleration after 3 seconds is 152 meters seconds to the minus 2. That, of course, is a very large acceleration. Rockets are capable of such things. Still considering the motion of the firework rocket, part C, give a physical reason for why the equation only holds for the first 3 seconds. The answer is the firework rocket would have run out of fuel after those first 3 seconds. Now give a mathematical reason for why the equation only holds for the first 3 seconds. Well, if you look at the equations for displacement and velocity, it suggests that the displacement and the velocity continue to increase indefinitely with time. Now clearly that is impossible. Well, scholars, that brings us to the end of the first section of Unit 1. Kinematics relationships is now complete. I hope you enjoyed it, and once you've had a chance to practice using all the new skills you've learned, you'll be ready to move on to Section 2 of Unit 1. Until then, have fun.